All right, the first step to solving an equation, we're just doing really simple solving equations, is to locate the variable. Locate the variable. What am I talking about when I'm talking about a variable, though?
The letter.
The letter. Whatever the unknown is in that equation will be represented by a letter. And so we're just trying to make sure we know where the letter or letters exist in this equation. Step 2 is to use inverse operations to isolate the variable. Ooh, big words. All right, when I'm talking about inverse operations, I'm talking about the operations in math that undo each other. So if I asked you what the inverse of addition is, what would you say? Absolutely, it's subtraction. And how about the inverse of multiplication? Dividing or division. Very good, yes. Those are the inverse operations we're going to be using today. We'll learn about a few more throughout the year, but don't worry about that till the spring. And then I also said that we want to isolate the variable. What does it mean for something to be isolated?
By itself.
By itself or alone. Yeah, by itself. That's the end goal here, is to get the letter to be all the way by itself on a certain side of the equation so that we know what value it represents. That's the solving step, step 3. And then because we're great students, we're always going to check our work. It takes 30 seconds to check a question. You guarantee that you get it right, right? So let's look at this example problem.
It says it's
Mults for multiplying and div for dividing. Yes. All right. Our first example here is x minus 7 equals 15. Now there's a bajillion and a half ways to solve an equation. The way I solve an equation might be different from the way your 8th grade teacher taught you how to solve an equation, and if you like their way better, you're totally allowed to use their way. If you Google around and find a different way to solve an equation that you like better than what I taught you, cool, awesome, use it, great. But here's the way I like to solve an equation. I think it's the most easy. Yes, you can. So what you're going to do is you're going to draw a line through the equal sign to separate the left side of the equation and the right side of the equation. I like to make sure all of my variables end up on the left side, which means all the numbers need to end up on the right side. What is currently on the incorrect side? What part of this equation is not on the right side? That? The negative 7? Cool, so we're going to take this negative 7 and we need to move it to that side. This is where inverse operations come in, because what's the operation I have to use to move it over there? Addition, the opposite of subtraction, yeah. So I'm going to actually add 7 to the other side to move it, which would mean I'd have x equal to 15 plus 7 as my equation now. Well, 15 and 7 are just good old-fashioned numbers. I can just straight up add them. What is 15 plus 7? 22. Is the x isolated? Yeah, it's all the way by itself. There's no coefficient. There's nothing else on that side, and so we're done. Number 2 is not going to be much harder. It's x plus 10 equal to 57. So we draw our line down the center of the equal sign to separate the two sides. That's to help organize our brain. And what is on the incorrect side? The 10. So if I take that positive 10 and I move it over here, what's the opposite of adding 10? Absolutely, subtracting 10. So now my equation should read x, no more 10 because we moved it, equal to 57 minus 10. Well, 57 minus 10 is, those are just easy numbers that I can do in my head. What's 57 minus 10? Absolutely. X is all the way by itself. It is isolated. So we have our solution. Now here's the thing. I forgot to be a good student. What did I forget to do in these two problems? Check my work. What does it mean to check your work?
You gotta put it in the variable.
Absolutely, we got to plug it in. So instead of writing x minus 7 equals 15 in number 1, what am I going to write in place of x?
You gonna put 40? Oh wait, we doing that one?
Yeah, sorry, I went back to number 1.
Okay, you gonna do
22 minus 7 equals 15. 22 minus 7 are good old-fashioned numbers. If I do that in my head, calculating, 22 minus 7 is 15. 15 equals 15 is a true mathematical statement because, yes, 15 is 15. If we happen to get any other number besides 15 when we did that subtraction problem, we'd know we made a mistake somewhere and we got to go back. So if it says 14 equals 15, that's an incorrect mathematical statement. We go back and we fix it. Let's check number 2. Instead of writing x plus 10 equals 57, what am I going to do to check my work? 47 plus 10 equals 57. Well, 47 plus 10 is 57. We know that. And 57 equals 57. Woohoo! True mathematical statement. Moving on to the next two types of inverse operations here. We have 8y equals 72. What's currently happening in that equation? 8 and a y are together, which means we are multiplying. Do y'all know why we're multiplying when two letters are stuck next to each other?
Because that just means that means you're, I don't know, but it means you're multiplying.
It does mean you're multiplying. Here's a fun fact of the day, kind of off topic, but I'm going to tell you anyways. In elementary school, you learn multiplication, and you learn multiplication like this. Do you agree?
Yeah.
5 times 6.
Now we're just taking out the eggs.
Right, because the reason we did that is because when we got to algebra and we started using unknowns, isn't that confusing?
Yeah.
5 times x. I'm like, what's the double x going on? So then in elementary school, you learn this notation. Do you agree?
That's the.
It's still multiplication. And so we can do that with variables. But I'm going to let you in on a little secret. Mathematicians are super lazy. If we can create a notation that's faster to write, we will, which is how we've gotten to math as it is now. So instead of writing all of that, mathematicians just took the 5 and the x and they stuck them next to each other. And they're like, cool, that means multiplication, because I'm too lazy to write anything else. Now, if I did that with straight up numbers, what's the problem with smushing two numbers together? It looks like 56. So what do we do to indicate that that's actually 5 times 6 when we the dot or parentheses? Y'all remember doing that sometimes? Okay, so that's the reason we do that, is because we want to really just smush those together to be lazy, but they're numbers and we're going to get confused and think it says 56. So we put the 6 in a parentheses, or put the 5 in a parentheses, and we know it's multiplication. Cool. Random tidbit of fact. That's why we put 5x together to mean multiplication. Let's go back up here. Oh, things didn't erase. It's fine. We're erasing. All right, so we know right now that 8 and y are multiplied together. So how do we undo multiplication? Dividing. So if we want that 8 to go over there, we need to do division to get it to move to the other side. And what we do on one side, we got to do on the other. 8 over 8 disappears because 8 over 8 is 1. They cancel each other out. We're left with just y equal to whatever 72 divided by 8 is, 9. Which is 9. The y is all the way by itself isolated, and so we have our solution. But we're good students, so we check our work. Can I write this to check my work?
No.
What did I forget to do? The dot or parentheses. Yeah, I'm going to put parentheses. That's good math habit. And now I can double check if 8 times 9 is 72. Well, 8 times 9, yeah, 72 equals 72. Check. I got it. Here's another one of my pet peeves. Y'all know this symbol right here?
Oh, the crusty symbol there.
Ooh, I hate it.
Don't we?
I hate it. Did y'all know that this is really just a placeholder for fractions? Yeah. The dividing sign is really just saying, hey, put a number here and put a number there, and you've got a division problem. Oh, wait, that's a fraction. Okay, so really what we are wanting to do when we do division problems is really look at them as fractions, or look at fractions as division problems. Now I say that because when we're solving number 4, we have k divided by 4 equal to 13. It's a fraction, but fractions are just division. So what's the opposite of division? Multiplication. And what am I going to multiply both of these sides by to get that 4 in the denominator to go away? 4. What I do to one side, I got to do to the other. But what do I have to do with the 4 on the right side there? Indicate that we're multiplying and that it's not 134, that it's really 13 times 4. Yeah, undoing division, the inverse of division is multiplication. So if we have a fraction, we have division. The 4's cancel out the same way the 8's did, and we're left with just k equal to whatever 13 times 4 is. Challenge question. It's beyond the range of what you probably learned in your multiplication tables, but who knows what 13 times 4 is?
13 times 4?
I heard somebody. 52. Absolutely. Good job. You rock. 52. But we're good students, so we check our work. Instead of writing k, I'd plug in a 52 divided by 4, or 52 fourths, and we're hoping that that's 13. 5 divided by 4 is 1 with 1 left over. 12 divided by 4 is 3. 13 equals 13. Takes 30 seconds to check it, especially when you have a calculator, and we have guaranteed ourselves that we got the correct solution.